For decades, we've been searching the cosmos for planets like Earth. Billions of dollars, thousands of scientists, entire space missions dedicated to one question: are we alone? And here's what we found: planets are everywhere, trillions of them. Earth-sized worlds, common. Planets in the habitable zone, we've found hundreds. But here's the twist that's keeping astronomers up at night. We've now catalogued over 6,000 planetary systems across the galaxy. We've studied their architectures, measured their orbits, analyzed their compositions. And you know what? We've never found another solar system that looks like ours, not even close. 0 confirmed systems, with small rocky planets in the inner region and gas giants in the outer region, arranged the way ours are. Not one. So either we live in the rarest solar system in the entire universe, or we're about to discover that systems like ours are hiding everywhere, and we just haven't been looking the right way. The answer is coming in December 2026, and it has profound implications for whether life is common in the cosmos or whether Earth might be truly, cosmically alone. Before we dive in, quick housekeeping. The YouTube algorithm has been, let's say, challenging lately. The absolute best way you can help this video reach more people is to like it and drop a comment. Even just interesting helps more than you'd think. Both actions together really signal to YouTube that this matters. And if you're new here, welcome. Hit subscribe, turn on notifications, and introduce yourself in the comments. Tell us where you're watching from. We've built an amazing community here, and we'd love to have you. Now let's talk about why our solar system might be the cosmic equivalent of winning the lottery. Take a look at our solar system. Really look at it. 4 small rocky planets hugging the Sun: Mercury, Venus, Earth, Mars, then a massive gap, the asteroid belt, and beyond that, 4 giant planets: Jupiter and Saturn, enormous balls of gas; Uranus and Neptune, ice giants lurking in the outer darkness. This arrangement seemed normal, obvious even. For centuries, we assumed this is just how planetary systems form: rocky planets close in where it's hot, gas giants far out where it's cold. Simple physics, right? Wrong. In 1995, Swiss astronomers Michel Mayor and Didier Queloz announced something that broke astronomy. They'd found a planet orbiting the star 51 Pegasi. Great, our first exoplanet around a sun-like star, except it was insane. The planet, dubbed 51 Pegasi b, was a gas giant, half the mass of Jupiter, but it wasn't orbiting far from its star like Jupiter does. It was practically skimming the star's surface, completing an orbit every 4 days, 4 Earth days. Jupiter takes 12 years. We called these hot Jupiters, and at first we thought maybe they were the weird ones, freaks of nature, but then we found more, and by the early 2000s, most of the planetary systems we knew consisted of these massive gas giants orbiting incredibly close to their stars. I want you to imagine being an astronomer in 2004. You grew up learning that our solar system was the template, the model, the way things work, and now you're looking at data showing that almost every other system looks completely different. The question shifted from, are there other planets, to, are there other solar systems like ours? Everything changed in 2009 when NASA launched the Kepler Space Telescope. This thing had one job: stare at one tiny patch of sky, just 1/400 of the entire sky, and watch 150,000 stars continuously for years, looking for the tiniest dips in brightness that might indicate a planet passing in front of its star. And Kepler delivered. By the mid-2010s, we were discovering hundreds of new planets every year. The catalog exploded. We found planets orbiting binary stars, planets around dead stars, planets made of diamond, planets covered in lava, planets where it rains glass sideways. But here's what really messed with our understanding. Most systems looked nothing like ours. Instead, they had what astronomers started calling peas in a pod configurations. Chains of similar-sized planets, all roughly the same mass, all orbiting relatively close to their star. Remember TRAPPIST-1? 7 Earth-sized planets, all packed into an orbit smaller than Mercury's. Or the super-Earth systems, planets slightly larger than Earth but smaller than Neptune, lined up like beads on a string. What we almost never found: a system with small rocky planets in the inner region and massive gas giants in the outer region, with clear separation between them. Astronomers started crunching the numbers. Based on Kepler's data, we estimate there are roughly 11 billion Earth-sized planets in habitable zones around Sun-like stars in our galaxy alone. 11 billion potential Earths. But how many of those are in solar systems that actually look like ours? We don't know, because until very recently, we literally couldn't detect them. To understand why solar system-like systems are so hard to find, we need to talk about how we find planets in the first place. There are three main methods, and each one has a blind spot that matters. Method 1, radial velocity, also called the Doppler method. Here's the thing: planets don't actually orbit stars. Stars and planets orbit their mutual center of mass, called the barycenter. It's always close to the star because the star is so much more massive, but the star does wobble. We can see that wobble as a tiny shift in the star's light, stretching toward red when it moves away from us, squishing toward blue when it moves toward us. The Doppler effect, same thing that makes an ambulance siren change pitch as it passes you. This method is fantastic for finding massive planets close to their star because they make the star wobble fast and noticeably. It's how we found those early hot Jupiters. But here's the problem: Jupiter-like planets in Jupiter-like orbits, they make stars wobble slowly, really slowly. Jupiter takes 12 years to orbit the Sun. So yeah, the Doppler method can eventually detect them, but it takes patience. Lots of it. And it's not great for the initial discovery phase where you're scanning thousands of stars at once. Method 2, the transit method. This is what Kepler used. Watch a star continuously and look for tiny, regular dips in brightness, mini eclipses, as a planet passes in front of it. This is brilliant for surveying lots of stars at once. You just point your telescope and watch. But there's a massive constraint: you need to see at least 3 transits to even confirm a candidate planet, 3 times across the face of the star. Kepler operated for about 4 years of prime mission time on any given star. That means it could potentially detect an exo-Mars. Mars takes about 2 years to orbit, but definitely not an exo-Jupiter. Jupiter's 12-year orbit. Kepler would have needed to run 3 times longer just to catch 3 transits, and that's assuming the planet's orbit is even aligned so we can see transits from Earth. Most aren't. The TESS satellite has picked up where Kepler left off, and it's doing amazing work. But we're still looking at decades of observation time needed to confirm Jupiter analogs through transits alone. So here's where we are. We've found thousands of exoplanets. We know Earth-sized planets are common. We know Sun-like stars are common. We've even found a handful of Earth-sized planets in habitable zones around Sun-like stars. But Jupiter, that's the missing piece, and it might be the most important piece. Some planetary scientists think Jupiter was absolutely critical to the development of life on Earth. It's massive enough that its gravity acts like a cosmic vacuum cleaner, sweeping up or deflecting comets and asteroids that might otherwise pummel the inner planets. Less bombardment means more stability. More stability means more time for life to get started and evolve without getting reset by extinction events every few million years. There's also the grand tack hypothesis, this wild idea that Jupiter actually migrated inward toward the Sun early in the solar system's history, disrupting the formation of larger planets in the inner system before retreating back outward. This might explain why Mars is so small and why we don't have super-Earths like most other systems seem to have. If that happened, and if it required some unusual circumstances, maybe a close pass by another star, maybe a specific timing of formation, then systems like ours might be genuinely rare. But again, we don't actually know if they're rare. We just know we haven't confirmed any, and that brings us to the game changer. In 2013, the European Space Agency launched something special, the Gaia Space Telescope. Its mission: to create the most detailed 3-dimensional map of our galaxy ever made. Gaia spent over a decade, from 2013 until March of this year, scanning the entire sky over and over again, making precise measurements of over 1 billion stars. 1 billion. Gaia's superpower is astrometry, the science of measuring the exact positions of celestial objects with mind-bending precision. How precise? Gaia can measure positions to within the angular size of a US quarter sitting on the moon as seen from Earth. Let me say that again. If you placed a quarter on the lunar surface, Gaia could track its position from 240,000 miles away. Gaia's primary goal was measuring stellar parallax, the apparent shift in a star's position as Earth orbits the Sun. This lets us calculate precise distances to stars across the galaxy, but here's where it gets interesting for planet hunting. If Gaia can see a star's apparent wobble due to parallax, it can also see a star's actual wobble due to the gravitational pull of its own planets. Remember how I said planets and stars orbit their mutual center of mass, that barycenter? The distance of that barycenter from the center of the star depends on two things: the planet's mass and the planet's distance from the star. Here's the beautiful part. Planets with larger orbits actually pull the barycenter farther from the star's center than planets with smaller orbits, even if they're the same mass. This makes the astrometry method more sensitive to distant planets, whereas both the Doppler and transit methods work better for close-in planets. It's the opposite sensitivity. It's perfect for finding Jupiter analogs. In 2023, astronomers announced Gaia's first confirmed exoplanet discoveries using astrometry, Gaia 4b and Gaia 5b. Both are super-Jupiters, 12 and 21 times Jupiter's mass respectively, orbiting nearby low-mass stars. The painstaking work of finding these two planets proved something crucial. Gaia can spot gas giants far from their stars. Where there's one, there are many. And that brings us to December 2026. Gaia Data Release 4, Dr. 4 for short. This will be fundamentally different from previous releases because for the first time, it'll include Gaia's complete time series measurements of stars' positions across the sky, not just the final parallax calculations. Dr. 4 will also span 5.5 years of observations, about twice as long as the previous data release. This extended baseline lets Gaia detect planets farther from their stars because these planets take years to complete an orbit, and Gaia needs to see enough of that orbital motion to confirm the planet's presence. Researchers Caleb Lammers and Josh Wynn from Princeton recently published a study predicting exactly how many exoplanets Gaia Dr. 4 will reveal. Based on simulated Gaia data accounting for the mission's sensitivity and the expected population of planets, they predict around 7,500 exoplanet detections, give or take a couple thousand. 7,500 planets. To put that in perspective, we've currently confirmed about 6,000 exoplanets total. Gaia Dr. 4 could more than double the known exoplanet population in a single data release. But that's just the beginning. Gaia Data Release 5, expected in the early 2030s, will include the full dataset, 10.5 years of astrometric measurements. The longer time span makes Gaia sensitive to planets with even longer orbital periods, more distant planets with larger orbits, which means larger stellar wobbles that can be detected over greater distances. Lammers and Wynn predict Dr. 5 will include approximately 120,000 planet detections. Let that sink in. 120,000 planets. That's a 20-fold increase over our current exoplanet catalog. But here's the real question. Will Gaia find solar systems like ours? Gaia will be sensitive to Jupiter-like worlds and super-Jupiters with orbits between 1 and 5 astronomical units from their star. An astronomical unit is the Earth-Sun distance. Jupiter sits at 5.2 AU, so Gaia should be able to spot a true Jupiter analog. It won't be sensitive enough to detect the wobble from Earth-mass planets, but that's okay, because we have TESS. The Transiting Exoplanet Survey satellite is observing a significant chunk of Gaia's target stars, searching for transits of smaller, inner planets. The combination is powerful. TESS finds the Earth analogues in the inner system through transits. Gaia finds the Jupiter analogues in the outer system through astrometry. Together, they give us something we've never had before, a comprehensive census of complete planetary systems, inner and outer regions, all in one picture. When Gaia flags a candidate exoplanet, astronomers follow up with radial velocity observations from ground-based telescopes, Doppler measurements that confirm the planet and better characterize its orbit and mass. It's a multi-method approach, each technique covering the weaknesses of the others. This flood of new data will revolutionize our understanding of how planetary systems form and evolve. For gas giants, we'll finally be able to test whether they form more like terrestrial planets, building up from small chunks of material that gradually clump together, or more like stars, with a large cloud of gas collapsing all at once. We'll see whether planetary migration is common or rare, whether systems naturally form with peas in a pod architecture, or whether our solar system's diverse architecture is actually normal and we've just been looking at biased samples. And maybe, just maybe, we'll find it, a true solar system analog, an Earth-sized planet in the habitable zone detected by TESS through transits, combined with a Jupiter-mass planet at the right distance, detected by Gaia through astrometry. Same star, same system, the cosmic twin of home. Or we won't find it. We'll catalog 120,000 planets, study thousands of complete systems, and discover that solar systems like ours are genuinely, profoundly rare. And if that's true, if we really do live in one of the rarest planetary architectures in the galaxy, it has staggering implications for the search for life. Maybe life isn't just about having an Earth-like planet in the habitable zone. Maybe you also need a Jupiter-like guardian in the outer system. Maybe you need a specific formation history that prevents super-Earths from forming too close in. Maybe you need all the pieces in exactly the right places, and those pieces almost never line up. December 2026. Mark your calendar. That's when Gaia data release 4 drops and we start getting answers. Are we common? Are we rare? Are we the galactic norm that's been hiding in plain sight? Or are we the cosmic lottery winner, a 1 in a trillion accident that happened to produce a world where life could ask these questions? For the first time in human history, we're about to find out whether the place we call home, this arrangement of rocks and gas giants, this specific architecture that gave rise to life and intelligence, is everywhere or nowhere. Either way, the answer will be beautiful and terrifying and profound. If you want to follow this story as it unfolds, hit subscribe. We'll be covering the Gaia Doctor 4 release and what it reveals about solar systems like ours. Drop a comment with your prediction, common or rare. I'm genuinely curious what you all think. Thanks for watching, and remember, whether we're common or extraordinary, we're here, we're asking, and that alone is pretty amazing.